Good
Good
evening.
evening, Professor.
Good evening,
Good.
Professor.
I hope you can hear me okay. I'm at a new location.
Good evening, sir.
Very good evening. Okay. Thank you so much. We'll wait for a couple more minutes while people join in and then get started.
Look like you're in my neck of the hood, Professor. Are you in a Bay Area?
I'm so sorry.
You look like you're on my neck of the hood, Bay Area. I see the Golden Gate Bridge.
Yes, that's the background. I am still in Hyderabad.
All right, good. Let's see.
In South Central India.
Okay, got it.
The background is always so deceiving, isn't it?
I'm sorry.
The background is always so deceiving. My background is Singapore.
Yes. So, which location are you joining from?
I'm in Singapore.
You are
I
in
stay in the eastern part of Singapore. But the background is, well, in the central part of Singapore.
Yes, yes, the iconic uh, location.
Yes.
Yes.
Good evening, Professor.
Good evening. Good. It looks like we have about 37, 38 people in the class. So let's get started. We are also 5 minutes into the class, so I don't want to wait too long. Pleasure to be here again with you all. We are continuing the regression class from yesterday. We have about 15-20 minutes of regression left. So we'll start with that. And then we move to today's topics, which are nearest neighbor learning. The method is commonly referred to as KNN, K nearest neighbor. And we'll also look at decision trees today. So those are the three topics that we will try and cover today. The major topics are going to be, the majority of the class is going to be taken up by the nearest neighbor in decision trees. But I think even for regression, we might spill over to about 30 minutes or more. Let's see how much ever time it takes. What is important is that you get it fully. Before we get started, does anybody have any leftover questions from the about the assignment? Any further questions on the assignment? Okay. If you think of any
No.
questions, yeah, go ahead, please.
I say no.
Okay, okay. In case somebody thinks about any more questions on the assignment, please feel free to ask them at any point of the class. It's important that you have full clarity on the assignment. Okay. Let's go ahead with the regression then. We were talking about linear regression. And on this slide, the concepts of linear regression are summarized. So there are a set of values that are given. These are, this is the training data. There are, there is an independent variable. Here we are showing simple linear regression, not multilinear regression. The feature X is the independent variable and feature Y is the dependent or target variable. And I was just looking at the chat window. The question is already answered, so I'm not answering. There is no group assignment. So X is the independent variable, Y is the dependent variable. Some points, X, Y combinations are given. So for example, X could be the age of the person and Y could be the height of the person. So age and height are given, let's say, as values. So each point is a two-tuple, which is the independent and dependent variable. So it can be plotted on a two-dimensional plane. And our purpose is to describe the relationship. Our goal is to describe the relationship between the independent and dependent variable in terms of a linear equation. The linear equation looks like y equals beta 0 plus beta 1x. Beta 1 is the slope of this line. Beta 0 is the intercept. So y equals beta 0 plus beta 1x is the equation that we want to learn from all of this data. And this data may not perfectly fit a line, but sometimes it may be more or less linearly describable, this relation. So for problems where the relationship is linearly describable, linear regression would work well. If the relationship is not linearly describable, then we might change our features. We might do feature engineering. For example, instead of x, we might take x squared. Instead of x, we might take some variation, some function of x. And then we might get a linear relationship. That kind of regression studies are also common, where you do some feature engineering or feature discovery before you find the linear relationship. And obviously, when you look at these points, I hope you're able to see that there are many possible lines that could be fit, of which one would have the lowest error. Now, how do we define the error? The error is defined as the distance of the points from this line. So when you substitute the x coordinate of this point into y equals beta 0 plus beta 1x, then there is a certain residual that comes in. Sum of all residuals, or sum of squares of all residuals, we can take a different, we can take either L1 error or L2 error. L2 is sum of squares of all the residuals. L1 would be sum of absolute values of all the residuals. whether the residual is positive, which will be true for the points above the line, and negative, which is true for points below the line, you take their absolute values and add it up, then that would be your total error. That error we are trying to minimize. For every location of the line, there is an error, and we do a gradient descent to find those values of beta 0 and B1, which will minimize this error, minimize the mean squared error. The mean squared error here is called the loss function. So our goal is to minimize the loss function. And the method that we use to minimize the loss function is gradient descent, okay, which is a well-known method. And the only other point is that this is for labeled data. So we do look for target variables. So we don't do this, for example, between two independent variables. Regression, we assume that on the left side of a regression equation, there is a target variable, and describe it as a linear summation of the independent variables or input variables, target and input. So if there is more than one independent variable, it will be called multiple linear regression. Okay, multiple linear regression. All these are concepts that I talked about yesterday. I'm just refreshing your memory on that. Now let's move forward from these concepts. So what we are looking for is, before I go to this slide, Mr. Sukesh has a question. Professor, why do you say dependent and independent variable? Both weight, height versus age are dependent, isn't it? Or age is something which is not under control. It's independent and dependent are context sensitive adjectives. There is no absolute independent and absolute dependent variable. So for example, if we are trying to, let us say, predict the weight of a newborn baby based on its height, based on his or her height, predict the weight of the baby just to see if the baby is malnourished or baby requires some kind of a intervention. This is a common thing that is done. We look at a few things like the diameter of the head, the height of the baby, etc. And on the base of that, we try to predict the weight. If there is no possibility of having a scale there, to measure the weight of the baby wherever the baby is born, across a country. If there is, a scale is not available, it is possible that you measure these few variables like the height, diameter of the head, diameter of the hip, etc. And then from that, try and predict the weight of the baby. In such case, the weight will be a dependent variable, and all the variables that you are using for prediction will be called independent variables. But in some other problem, weight could become an independent variable, where taking the weight of the baby also into account, you're trying to classify the babies as potentially malnourished or not malnourished. You may take the weight of the baby as an independent variable. So the definition of what is an independent variable, what is a dependent variable, is problem dependent. Okay, I hope that makes sense to you.
So basically, you are saying the outcome in this case, whatever y is, that is a dependent variable.
Correct.
And all the input parameters what we give, x1, x2, x3, or whatever it is, those are all independent variable which which may affect or may not the y parameter.
Perfect, Mr. Sukesh. Inputs are the independent variables as we define it here, and the output or target variable is the dependent variable.
Yeah, thanks.
Yeah. Mr. Krishnamurthy, can we consider gradient descent as an error correction mechanism? No, Mr. Krishnamurthy, we are not correcting any error. We are only looking at multiple possible lines. Let's go back here. So this is one possible line, and we might, draw another possible line like that, another possible line like that. And between all these various possible lines, we want to find the line that minimizes the error. And that's the reason we are doing gradient descent. So it is a search or optimization mechanism, not an error correction mechanism. Okay. Okay. So let's move on. So our goal is to build a regression machine. Essentially, in regression, our goal is to build a machine, machine in the sense, and a model builder, which takes relevant sample data. And this sample data is, from your raw data, you have already done your exploratory data analysis and discovered some characteristics of the data. You have then done some data cleansing. For example, if there is missing data, then you have filled it up, filled up the missing values with, let us say, averages of some attributes, etc. You have removed the noisy instances, you have removed the outliers, and then you have done feature engineering if necessary. In some data sets, the raw data, for example, if you go to a bank and get a raw data about a customer, it might just be transaction data, or what products of the bank the customer is using, etc. From the transactions, you may want to get some derived data set, derived features, like how much are they spending on average per month, how much are they, what is the year to year increase or decrease in the amount of business they are giving the bank. These are derived features that you can compute from the raw features given to you. So this discovering derived features will be part of feature engineering. So take your raw data, put it through all the exploratory data analysis and data cleansing. And finally, after you get a curated data set with class labels, divide it into training data, validation data, and test data, and you pass the training data into the regression model builder. That is this arrow. On the other side, you say that, I would like a regular multiple linear regression. That is, I want to consider all of these variables. Or you might say, I want a lasso regression. I want a ridge regression. I will define these terms as we go forward. And we, whatever are our configurations for the regression and model, those configurations, those settings are going into this arrow. These two are the inputs to the regression machine. And what comes out is a regression model. And the model looks like, if it is linear regression, the model looks like a linear equation like this. There is an error term. Typically, this error term you will compute. This is the residual. We can compute after we have the model. So you're not actually computing this through the model builder. But your independent variable is on this side. Your intercept term is here. This is your beta 0 plus beta 1 times mileage, beta 2 times age, plus beta 3 times make, whatever. I know this is an automotive example, as you can see. So whatever are the variables, we have coordinates, coefficients for each of them. And these coefficients are the ones that are computed through gradient descent. So the regression machine takes the data and some method configuration and outputs an equation like this. This is what is the engine that is giving you the regression model. Now, you may say that here that I want linear regression, I want multiple linear. This one is multiple linear regression because there are multiple independent variables. So here you would have said multiple linear regression. And in another case, you might say logistic regression. We'll also talk about logistic regression shortly. So this is the, I hope it's clear to everybody. I'm saying this explicitly because we are talking about the type of the model, which is regression. Later, we'll talk about a type of the model, which is nearest neighbor, KNN. Another type of the model is decision tree. We talked about these types yesterday. We said each type corresponds to a particular shape. Regression, linear regression corresponds to a line that you're fitting in k dimensions. Nearest neighbor, KNN, has no decision surface. It only finds the nearest examples for the test sample that comes in. Decision tree tessellates the space in hierarchically into axis parallel rectangles. So the shape defines the type of the classifier, and then there is an engine or a model builder which will give us the that type of classifier for a data set. So this will be the sort of tree builder or regression builder, SVM builder, neural network builder, etc. So that's the search and optimization method which will give you the final classifier. And this engine works on the basis of gradient descent for regression. Mr. Chan says, what are the relevant assumptions of regression machine? What should we do if we discover that the variance of regression errors is not constant? Yes, the assumptions, I will touch upon them shortly. Linear regression does not work on every kind of problem. On some problems, directly it has a good result. On others, it can have a good result if you do feature engineering appropriately. But for some more problems, even if you do feature engineering, regression may not be able to give you a good, good classifier. This is because if the underlying, data, underlying decision surface is not linear, or even if it is, even if it is linear, if the underlying if the underlying classifier is not linear, let's just stick to that case, is very non-linear, is complex and non-linear, then no matter what you do with feature engineering, regression will not be able to find you the right solution. So the short answer for Mr. Chan's question is that if you discover that regression is not able to produce good results on your data set, then you would apply the other methods which are capable of finding nonlinear surfaces, like nearest neighbor. KNN can find nonlinear surfaces. Or it doesn't have a surface, but implicitly it can be nonlinear. I will explain what I mean when we talk about KNN. SVM can directly find a nonlinear surface. Artificial neural network can directly find a nonlinear surface. So we will use models like that in places where regression doesn't work. In some problems, when you discover that the variance of regression errors is not constant, then it is possible to pre-process the data such that you make the variance uniform or constant, in which case regression will become helpful. And this is done through feature engineering. Okay, we'll look at the assumptions in shortly. Ms. Raghuram.
Yes, Professor. I was just wondering, like, just taking a little from what the earlier discussion was, that we would need to first take a call on what kind of data we have, and therefore what could be the possible regression model or models, and hence, pass it through the model builder to come up with the coefficients for a good fit for the data that we have. Is it possible that a particular model builder can actually consider more than one or multiple regression models so that it kind of reduces your time and it
Yes,
does the computation simultaneously and comes up with the right model or algorithm.
absolutely, ma'am. That class of algorithms typically are referred to as AutoML. So there are multiple AutoML methods which will have multiple classes. Each one of those tools will have multiple classes of algorithms that it supports. And, automatically it can go through all those classes of algorithms and compare them on a validation set, performance on a validation set, and come back to you saying, for your data set, K nearest neighbor seems to be the best, seems to give the best results, or SVM seems to give the best results, and so on. So in fact, more often than not, today, ML engineers do not have to, manually try each of the methods. We can put it through a longish run where it considers a dozen different models, the model builders, goes through them and comes back to you with whatever fits your data the best.
What about feature engineering? Can that also be done without a manual?
Feature engineering, doing feature engineering without manual intervention is the primary purpose of deep learning, ma'am. So deep
Okay.
learning exists for that. There is no feature engineering we do in deep learning. It will discover the features automatically.
Okay. Thank you.
Okay.
I think someone had a chat, someone else had a point saying that, wouldn't AI be the best way rather than ML for ensuring that, we
Yes,
don't have
Mr.
to.
Manji. Yes, I'm going to answer that.
Right,
Mr. Manji, what happens when what we call as AI today is essentially deep learning. These are deep neural networks, and with different architectures, and we'll talk about those architectures in the deep learning class. And these, so there is, yes, you can find out a model using a deep learning network, not a regression model, but a black box artificial neural network model which has a nonlinear decision surface. You can definitely discover that using AI, but it's not equivalent to AutoML. A neural network is not trying out a decision tree, a KNN, etc. It's not trying out multiple methods and coming up with a best possible solution. Neural network is also one more algorithm, because today those deep learning networks are so so large and sophisticated because they have billions of parameters. They can discover any concept that is underlying a data. They can approximate any concept that is underlying the data. So they tend to have a good performance. But your problem might be that your data actually, you have done feature engineering so well, you understand your domain so well that a simple classifier would have served your purpose. But when you apply a transformer based LLM to it, which you're calling as AI today, then you may end up discovering a large complex model whose running costs are so much more than what a simple decision tree might have given you. So AutoML has the advantage of considering symbolic machine learning methods. So if there is a simple solution available, AutoML will discover it. Whereas an AI, even if a simple solution is available, might end up modeling it with many, many parameters. That's why AI may not replace AutoML. Okay, Ms. Mike, thank you. Ms. Micah says, I have a question about how this applies in the real world. If I'm consulting for a client as a DBA, am I expected to actually build regression k-nearest neighbor decision tree models myself, or am I learning these methods so I understand what the team is doing, can ask the right questions, help customers choose? Okay. In fact, Miss Micah, that's a great question and it's useful to everybody. I think where the field is evolving, in general, workplaces are evolving to a human using dozens of tools or hundreds of agents to multiply their productivity. So I'm imagining that there, just like we have let's say, I'll take an example and then talk about data science. Example, let us take a visual designer. Today, somebody who who is able to do visual design, we expect them to convert into a creative director. So they not only should be able to do the design using some AI tool, but they should be able to understand the requirement of the customer, come up with a wireframe, do the discussion with the customer to know what refinements to make, and then produce the final output that the customer might like, and do it at scale. Produce something that can be just directly put on the website for fast loading, or on a mobile phone or social media, whatever, in multiple formats, produce the same design. So a creative director has an end-to-end responsibility, whereas a visual designer has a point responsibility. Similarly, an ML engineer today has a point responsibility. But as a DBA, I think as the AI tools evolve, as the library tool availability, LLM availability, Gen AI availability, agent availability increases, a DBA will be able to do this end-to-end task of coming up with a solution. So talking to the customer, understanding their problem, very quickly playing with their data, using an AI engine to clean up the data, prompting it right to clean it up, and then using different types of models to different types of model builders and tools to build the models, like an auto ML. I'm not talking about each algorithm being done separately, but you would use a tool that would go try out multiple algorithms, get the best possible model, understand how to explain it to your customer. So, figure out the explainability. And once the customer agrees on it or refines it, then, putting it into deployment. So a DBA, at least at a high level, needs to feel comfortable with a cycle like this. You may have a team which you may use for parts of this cycle, but I think overall visibility of the cycle, overall comfort with the cycle, needs to be there with you as a leader. Of course, if you are in a place where you're not even talking to customers, where let's say you're a CXO, you are only strategizing things and you have people that do this for you, then you will need to operate at a different level, which is, what kind of investments should I put into AI tools? What kind of people should I be hiring? Their KPIs, etc. You may have different, responsibilities, but a hands-on, um, a person dealing hands-on with machine learning as we progress next 2, 3, 4 years, I think will need to be able to play with this entire life cycle, from a customer brief to deployment. And that's the reason, in order to do that, you need to know what kind of tools are available, what you are doing, what does exploratory data analysis mean, what does model building mean, why are we building supervised versus unsupervised models or reinforcement learning models, etc. How do we deploy them? What are the considerations in deployment? Those things are needed, and which is what we are trying to cover in this course.
Thank you, Professor.
Thank you. Okay. So let's move on. Mr. Panala.
Hi, Professor. Good evening.
Hi, good evening.
Okay, this is a follow-up to what Micah was asking. Again, the same thing, right? At a level where we have a problem, we need to define a solution which would be typically a solution from an AI ML platform and all, and obviously we'll have teams in place. So coming back to the same thing, uh, this program is going to help us out to understand how to use an AI ML to define and to conclude to a solution. Definitely, uh, we're not going to start sketching this algorithms on our own, coding and all that thing, because it requires a different skill set, right? But
Yes.
yes, it will definitely help us to define a solution, which is the most important thing, because that's an outcome which we are looking at and our customer also is looking at, whether
Yes.
it's our own business or maybe a customer's requirement. Correct, no? This is
Yes, Mr. Deepak Verma. What you have said and what Ms. Maika has said, for your experience and expertise profiles, is absolutely suitable. There might be some people in the class, however, who have been algorithm builders. For them, there is an excitement of, let's say, being able to code up a whole neural network by themselves, and then play with it, see how they can perhaps take a mature model and improve it. That kind of, some DBA work has technical contributions, some DBA work has business contributions, so on. So what you said is perfectly correct. I just want to point out that there may be a variety.
noted, Professor. Thanks a lot. Thank you.
Thanks. So let's move on with it. I think all the labels that I have added now into the picture, they're clear. I have already said these things in words, so I'll move on. One of the things that is important while doing regression is a loss function. This is the function that you are that we are doing a gradient descent on. I'm showing a specific loss function here, which is mean squared error. It is also called the L2 error. 2 just signifies that we are squaring the distance here. So what we are taking is the difference between the predicted and expected values of the output variable. So you have done, you have assumed certain values for beta 0 and beta 1. So y equals beta 0 plus beta 1 x. Let's say that is your line. Into that line, when you substitute the value of x, and since you have taken values for beta 0 and beta 1, you can compute y. This y hat is what you have computed or predicted. And y is the actual data you already have, because this is a supervised data. You have been given the labels. So the difference between the actual and predicted values of the outcome variable, that difference we are taking and squaring it because the difference may be positive for some points, negative for some points. So you square it and add it up and divide it by the number of points. This summation is over n points. So we are dividing it by n to get average squared error or mean squared error. That is the L2 measure. And this is the most common, this is a common loss function that is utilized in regression problems. The definition of the loss function is one of the major determinants of success, both in regression and in artificial neural networks. The designing of the loss function is if somebody designs the loss function correctly for a problem, then the probability of success of that machine learning exercise is high. So design of the loss function is important. Regression uses some simple loss functions, but there are advanced regression users who come up with their own loss function definition. We'll see some complex loss functions as they are used in lasso regression and ridge regression. We'll see them in the next slides. So mean squared error is the most, is sort of the starting point. And it's very important in practical application. Solution can be easily obtained analytically because you have, loss function is, it has a derivative here. So you can actually find its slope. You can solve for this equation. So there is an analytical solution that you can get if you use mean squared error. That's why it's popular. It is not robust to outliers. In outliers, what happens is your y minus y hat becomes a very large value. Outlier is nowhere near the line you have drawn. So error is very high and it pulls up the entire line towards it. So you end up discovering the wrong line. So the problem with mean squared error is that it's not robust to outliers. If you had done, uh, sophisticated outlier detection as part of your data cleansing and gotten rid of the outliers, then you can use mean squared error. But if your data has outliers, then your mean squared error based regression may not produce good results. There are alternatives to this. L1 loss function, which is called mean absolute error, where you're not squaring, we are just summing up the absolute difference between the values here. This is not yi minus xi, I'm so sorry. This is the same yi minus yi cap. And then we divide that by the same n. So we are getting the average value, not of the square error, but of the absolute error. I will correct this before I share the document with you. It is yi minus yi prime square. The problem has happened because I cut and paste the formula from different locations. So this was a mistake. Then there is a third thing called Huber loss. And Huber loss is a mixture of mean square error and mean absolute error. You see square being utilized when the difference, when the error is small. And if the error is large, we use a absolute difference. The problem with square is if the difference is high, then you're squaring it. You're making it much larger. And hence it could influence your, final surface that you discover, final line that you discover. And Huber loss combines this in a good way. When the difference is small, it uses the square difference. When square of the difference. When the difference is large, it uses only the absolute value of the difference. And by doing so, it is more robust compared to mean square error and mean absolute error. So the point is that there is some loss function, and every location of the line has a loss function. Of all such locations, you are searching for the lowest loss function. And this is, if it is L2 loss, then it is differentiable. You can directly get to it. You don't even need to use the gradient descent. Whereas if it is, that's why I said regression is a very fast algorithm. If it is an L2 loss you're using, then it's a matter of computing the L2 loss and doing differentiation of that, and you can directly find out the parameters. But L1 loss is, does not allow such a thing. We need to, compute it in iterations. Like a gradient descent is an iterative algorithm. Analytical method can be a direct solver. Huber loss combines the theoretical strengths of the, of both. And practically, you start with L2 wherever possible because it has an analytical solution. Okay. I hope that's making sense to everybody. Let me see. Mr. Abdul Malak says, do we get the same result if we apply different models? If not, then we need to pick the right model from the beginning. Same result, Mr. Abdul Malak. By result, it depends on what we define as result. Model is not the result. The prediction is the result, right? So as long as your prediction is the same, let's say somebody is using rectangular decision surfaces to predict. Somebody is using circular decision surfaces. Somebody is using nonlinear amoeba-like locations to discover the labels or predict the labels. If all of them give you the same results, then you're okay. You're okay comparing models. And also, when we are building a model, we don't look at how the model classifies a particular instance. You're actually taking a whole validation data set and looking at the performance of the model on that data set. What percentage of the points did it predict the right labels for? That kind of performance you're looking at. So as long as the performance is comparable between different models, we are okay to use different models. We don't need to start with the models. We don't need to worry about whether the models have the same equations or not. We just need to worry about what their outcome is, what their prediction is. Okay, Ms. Raghuraman.
Professor, in Huber laws, how would you decide on what should the delta be in order to,
What should be?
The delta that, you have said if
Yes.
error is small and if error is large. So how do we
Yes.
decide when it is
So
small?
that's you remember on the regression machine, from one side, we have configuration parameters going in. So
Yes.
this is a configuration parameter that, you decide. So you will look at, you will, again, there is, for each of these parameters that you use, you can do a grid optimization. You can have a hyperparameter optimization that an AutoML algorithm does and give you the, a good value of delta to use. So your trial and error, empirical determination.
Oh,
okay.
Thank you.
Okay. Going forward, let's look at how logistic regression works. The primary difference is that linear regression is for predicting a value, whereas logistic regression is for predicting a class. Okay, logistic regression is a classification method, whereas linear regression is a regression method. We talked about the difference of both of them yesterday. So here, I have still an independent variable that is age. And I have a dependent variable, which is coronary heart disease. If you remember the same example, when we took for regression, our dependent variable was systolic blood pressure. That was a number. But presence or absence of coronary heart disease is what we are taking as the dependent variable now. So the dependent variable has only zeros and ones. It's a binary variable. As long as it is discrete, logistic regression can be applied. But let us start with a 0 and 1. Let's start with a binary. Discrete is, more than 2 values. Here, there could be 3 classes, 4 classes, and so on. But it's not continuous values. How do we analyze this data? Well, we can look at, perhaps a comparison of mean age of the deceased and non-deceased women, deceased and non-deceased women. That is, women with the heart disease and women without the heart disease. That's what we mean by deceased and non-deceased here. So the difference here, you can see, maybe can we use linear regression on this data? That is the first question we ask. And we obviously cannot, because the data looks like this. When we plot 0 and 1, 0 is the no here, and yes is the 1. So depending on the age, it is either 0 or 1. So you cannot draw, how do you draw a line between them? There is no value between no and yes. You cannot draw a line on the y-axis here to separate them. So we need to do something else. So one possibility, if we think numerically, one possibility is we can divide this age into groups and say between 20 and 29 years of age, there are 5 people in this group. Out of them, 0 are deceased. So there is a 0% disease probability in this age group, 20 to 29. Whereas 30 to 39, there is 17% probability. 1 out of 6 people has, so this is a pivot on the previous table that we have seen. We're just taking an age group and seeing how many of them have disease. And when you do that, the graph starts looking like this. And now if I'm plotting on y-axis, instead of the yes or no values, I am plotting this percentage. then I start seeing a pattern that looks linear, right? Start seeing a linear pattern. So that is what we are plotting in logistic regression. Let me show you again. This looks like a a curve which is logistic. The shape of the curve is a logistic here. So this is the shape of the curve, and this shape, if you look at what we are plotting, we are saying probability that somebody has a disease if they are in this age group. So probability of Y given X is what we are looking at. And we are only seeing, proportion here, not really probability in this strict sense of the word, but proportion and probability. If your data set is large enough, proportions do indicate probabilities. So in this particular data set, by counting and computing proportions, you're actually computing probabilities. What is the probability of somebody in the age group of 40 and 49 having coronary heart disease? It is 29%. That is 0.29. So on the right side here, you see the probability of Y given X, probability of coronary heart disease given the value, given X. X here is the age group that we are looking at. So this curve, can be described mathematically by this equation. So we are arriving at how to do logistic regression here. Let's say e to the power of k divided by 1 plus e to the power of k is what this curve is. Why the denominator here? Because we are capping the value of the function to 1. Okay, 1 should be the highest value, hence you must have a denominator. 0 is the lowest value, which this could be e to the power of x. Here, if x is 0, then e to the power of 0 is going to be 1, and 1 by 1 plus 2 here, it will be a 0.5 probability, which is random. So when you take x as 0, this will become a random guess. Whereas when you take, which means that you cannot come up with a probability there. Whereas in the maximum value that the function can take is 1. I'm just rewriting this now. This equation, if you rewrite, it will look like this. Alpha plus beta x is log natural of this function. Now I'm essentially doing, instead of doing an exponential calculation on the right side, I'm doing a logarithmic calculation on the left side. So these two functions are equivalent. If this kind of math doesn't make sense to you, it's all right. I am just deriving the logit function. This thing is called a logit of probability of y given x. So we are essentially plotting probability of y given x here. And that is the way to separate, that is the way to find out a linear classifier. Why is it a linear classifier? Because you have alpha plus beta x, classic linear formation here. So your classifier is linear, but you're computing it from the values that have been given to you. Probability of y given x, you're computing it there. So the midpoint is 0.5. When you give it a 0 value, like I said, midpoint is 0.5. When you give it a negative infinity, if you go back here and say that x is negative infinity, e to the power of negative infinity will be 0. So the curve, it tends to 0. And on the right side, the maximum value it can take is 1. So it always hovers between 0 and 1. X is minus infinity, y is 0. X is infinity, y is 1. X is 0, then y is 0.5. That is, the probability is random. So y always takes a value between 0 and 1 when x varies from minus infinity to plus infinity. So it is a probability number. Because it takes values between 0 and 1, what we are plotting is a probability number, y. And the advantages of this function, there's logit function, ln p over 1 minus p or 1 plus p, whichever. You could actually show that 1 plus p or 1 minus p are okay. We are doing 1 minus p because we know that p here is a is a number between 0 and 1, and we need to keep this between 0 and 1. So the advantage of this function is that this is just a simple transformation of probability of dependent variable given independent variable, and it has a linear relationship with x, and it is a known binomial distribution. This is a known distribution. This distribution is a very common one, and it is directly related to the notion of odds of the disease, or the notion of odds of the outcome. So it is directly a computation of odds. When you do a gambling, you may have seen in your probability class functions like this when people are talking about the odds of a game, odds of the output of a game. So this is directly related to that notion. So what we do in logistic regression is compute this function, this e to the power of alpha plus beta x, 1 plus e to the power of alpha plus beta x. This is what we use to compute the values of alpha and beta. Our whole goal is to compute the value of alpha and beta. Then we have a classification. So alpha and beta x will give you a towards 0 or towards 1 value, depending on, and you will set a threshold. If this value is alpha plus beta x is greater than a certain threshold, you will say that it is class 1, otherwise it's class 0, because alpha plus beta x is this odds. Okay, so if my odds are greater than 0.5, I will call it as class 1. If my odds are less than 0.5, I'll call it as class 0. This could be the thing. Or you may want to be more stringent. You can say if my odds are greater than 0.9, I will call it class 1. Otherwise, I'll call it class 0. Up to you. So when you are doing a logistic regression, you will, essentially compute the probability odds here. And there is also an equivalent of multiple linear regression here, which looks like this. Instead of having alpha plus beta x, you can have multiple independent variables and figure out their coordinates, figure out their coefficients. I'm so sorry, figure out their coefficients. So the interpretation of these beta 1, beta 2, beta j in linear regression, I hope you remember, the interpretation was how much does this attribute or feature influence the outcome? For unit change in this feature, what is the change that will happen to the output? That is what we were looking at in linear regression. Whereas in multiple logistic regression, essentially increase in the log odds for 1 unit increase in xi with all other xi's being constant. Increase in the odds. So if I just increase, let me go back to the our actual problem that we were solving, which has age. So if my age group goes from this bucket to this bucket, how much do my odds increase? That's what the beta parameter tells. The beta that you're multiplying, alpha plus beta x, the beta that is multiplying the age group tells what is the increase in odds or decrease in odds when there is a unit change in the age. And in multiple regression, when you go to an example like this, where you have low birth weight, age of the mother in years, weight of the mother in pounds, race, number of doctor's visits in the last trimester, if all of these are your independent variables, and your dependent variable is low birth weight, everything else is independent variable, age, weight, race, number of doctor visits. and low birth weight is what we are trying to predict. And this prediction is low birth weight is yes if the baby is less than 2.5 kg, or no if the baby is greater than or equal to 2.5 kg. So this is a classification problem, and we can use logistic regression. Essentially, logistic regression will give you an equation like this, which will have coefficients, which will discover coefficient values beta 1, beta 2, beta 3, beta 4, which give the importance of each of these variables in moving the log odds. Okay, moving the log odds. I hope this is making sense to everybody. Ms. Raghuraman, did you have it? You have your hand up from before, or is it a fresh question?
Sorry, it's a fresh question.
Okay.
Yeah.
No.
So
Yes,
if
yes, please.
thank you. If beta 1, beta 2, and so on are giving us how much odds, how much are the odds, right? For that particular variable to contribute to the outcome. Is there some way, I mean, does it also give us an idea about which variables to not consider? If I have taken up too many variables to consider, and then I find that beta 1 is, say, beta X or beta N is very, very low, then in future, I may not want to look at that variable at all and waste my time. Is it possible to do that?
Yes, absolutely. Regression is useful for that purpose. So let me start by saying that beta 1, beta 2 are not giving you what are the odds for the output given this variable. They are, it's a minor correction. They are giving what is the increase in the log odds if for unit change in this variable. So how much is, how sensitive is the classification output to this variable? That's what beta 1, beta 2 are giving. So let's say your final equation is, and I'm saying a hypothetical equation. Let's say your final logistic regression equation is 0.2, alpha is 0.2, beta 1 is 0.6, beta 2 is 0.3, and beta 3 and beta 4 both are values below 0.01. Okay, beta 1 and beta 2 are 0.6 and 0.3, whereas the beta 3, beta 4, because we have 4 independent variables here, are very small values. Then you, assuming that you have, analyzed your data, assuming that one of the variables is not far larger, its range is not far larger than other variables, assuming that you have done basic data cleaning well, a normalization well, then the value of the beta directly is a giveaway to how important that variable is to determine the low birth weight babies. So you, if your data is prepared right, regression coefficients, whether it is in linear regression or in logistic regression, are indicators of how important a given feature is in determining the outcome. How important, importance of the variable of that feature is directly proportional or dependent on the value of that coefficient, assuming that your data has been normalized. What do I mean by normalization? If your age range is between, let's say, 20 and 60, and if your salary range is between 20,000 and 100,000, then your y minus y cap, the mean square error computation, gets unduly affected by the salary. The age differences, because the range is only 20 to 60, they will matter very less compared to the salary differences. To avoid this problem, you need to first normalize the salary, bring it down to the same range. Let's say every variable you're bringing down to 0 to 1 range. That's a normalization. If you have done that normalization step earlier, then the beta values, the coefficient values, are a giveaway about the relative importance about that variable, relative importance of that variable in determining the outcome.
Right.
They can be useful
So
features.
the key is that you normalize ensure normalization and data cleanup before you take a
Absolutely.
stab at whether or not beta variable is important. I mean, that particular variable. Right.
Yes,
Thank you.
yes, it is. Mr. Kannan?
Doctor, I just want to understand how important it is to understand the
Yeah, I saw your
actual
question.
equation,
Yeah.
or I just need to understand there is one beta 1, 2, 3, 4, and there is a linear and logistic regression, and how does it work? Is that understanding what I need to have, or I need to understand the equation?
No, you do not need to, like, we have talked before. Today's ML engineering activity essentially involves running a few tools with maybe some parameter settings. So a high level understanding of the difference between linear regression and logistic regression, maybe the concept of odds, and it is doing some kind of a probability computation. That is sufficient. It's unless you plan to publish a paper on a variant of logistic regression and get into the math there. And there are people that might be interested in such things. It is not important for a general ML a DBA candidate to understand the mathematical equations thoroughly.
Super, Professor. Thanks a ton.
Yeah. Thank you. Ms. Micah?
Professor, are you saying arts? ARTS? What are you saying when you say arts? I heard you say arts a couple of times. What are you saying?
Arts?
Oh, maybe
What
arts,
sounded
arts.
like
It's
Just
odd.
said it not too
odds?
long ago.
ODDS, odds.
Odds. Thank you. Thank you so much.
Sorry for this. Yes.
No
Okay.
worries. Thank you.
Okay. Odds. Yeah. Um, Professor, similar to linear regression, what is the optimization method for logistic regression? I mean, we can still do a gradient descent because we now have probability space. So we can do a y minus y prime, and mean square error and so on. So similar, Mr. Chavan. And yes, thank you for others for having called out odds. Okay, let's move on. There is a parameter that you normally see in regression results, which is called R squared. And this is essentially the percentage variation in the output variable or the dependent variable, which is explainable by the independent variables. See, I have mentioned that some problems may be inherently linear. The relationship between independent and dependent variables may be inherently linear. In such cases, linear regression would work fabulously. Some problems, you may be able to do some feature engineering before and get a linear relationship between independent and dependent variable. Still, there the linear regression would work well. But if the relationship between dependent and independent variable is inherently nonlinear, then regression wouldn't do well. How do we know? If you run any data set with the regression engine, you will get a result. How do we know if regression worked on this data or did not work on this data? That you determine through this parameter called R square. It's written as R to the power of 2. I'm just writing it as R square so that you know clearly what I'm talking about. And this gives the percentage of variation in the output variable, which can be explained by the independent variables. So this is a value between 0 and 1. If it is 0, it means that y cannot be predicted by x. If it is 1, it means that y can be perfectly predicted by x. So it's 0 to 1. So the more R square value is, the more you know that linear regression is suitable for this, or logistic regression is suitable for this method. Okay, if in a classification problem, if there's a perfect linear separator between the yes class and the no class, then logistic regression will have a high R square. If the yes class and no class are so mingled up and there is a nonlinear surface between them, then R square value would be low. So just by looking at the R square value, you can determine, you can see whether regression is the right method for this problem or not. Okay. And we also have, and there is a easy way of determining this R square. It is essentially, it is determined from the mean square error calculations. I won't go into the calculation of R square now, but I just want you to know that when somebody shows you regression results, the first thing you need to look at is R square. See if R square value is closer to 1. If so, regression is the right method for this problem. If R square is hovering at a value that is far away from 1, then you know that maybe there are better methods to apply and not linear or logistic regression here. There is also a variant of R square called adjusted R square. The only difference between these two is that if many variables are insignificant, then adjusted R square takes that into account. It penalizes the insignificant variables. So you have if your data set may contain multiple variables that have no relationship with the outcome variable, and if you run a linear regression on it or a logistic regression on it, then your adjusted R square measure is a better indication of whether regression is working correctly or not than regular R square. Adjusted R square has an equation which takes into account the number of variables, etc. I won't go into the equations of how R square and adjusted R square are computed, but please remember these two terms, and the value should be between 0 and 1 for both. The higher the value, the more suitable the method, regression method for that data set. Mr. Chavan says, similar to linear regression, what is the okay, done. Okay. Mr. Upadhyay, is R square applies to only 2 variable scenario? No. R square applies to any number of variables. So when we say X value here, thank you, we do have an S in the parenthesis. So it is, multiple linear regression, multiple logistic regression, or simple linear regression, simple logistic regression, or lasso regression or ridge regression. Any of the regression methods will have an R square value. Now, about lasso and ridge regression, I use these terms multiple times. These are the result of, this is a small variation on regression where you're introducing this component of regularization. Regularization, the necessity for, or the rationale for adding this step is we want to, if, let's look at the values of beta 1, beta 2, beta 3, beta 4. Let's say beta 1, beta 2, beta 3 are hovering in the range of 0.05, 0.07, 0.08, in that range. And just beta 4 is huge. It is 0.99. I'm just making up a hypothetical example. So one coefficient is unnecessarily high, is too high, which means that it is essentially determining, all the effect of the, it's essentially determining the output variable. You don't want such things to happen. If you know, as a domain practitioner, you know that the other variables are also important, and it's a, a artifact of the method you're using. Then what you do is, to your, mean square error term, loss term, you add a penalty term. This penalty term is added in absolute terms here. So this is actually the beta parameters, the value of the beta 1, beta 2, beta 3, add those up and take the absolute values and add those up. This is a sum of all betas. And there is a, a hyperparameter here, which is the lambda. This hyperparameter, depending on where you set it, you will regulate the values of the betas that much. It won't let betas to become very large. because you are adding it to the term that needs to be minimized. The loss needs to be minimized. Now it is loss plus all the values of the betas that multiplied by lambda that you are trying to minimize. By doing this, you will regulate the values of the beta. You will, so weighing of penalty term gives an intuitive hyperparameter to control the model complexity. We want to ensure that model complexity doesn't become too high, and hence we are adding. I'll come to your question, Mr. Sukesh. If we add it in L1, if we add it as absolute values, then it results in lasso regression. If you add it in L2, where you are adding beta square, not just beta, where you're adding beta square, then it results in ridge regression. So if you run a regular regression, let's say regular linear regression, multiple linear regression, and you see that beta values are coming very high, then you may want to try out a lasso regression and ridge regression, running that. And all they're doing differently is the loss function definition. The use of gradient descent, all of that remains the same. Iterative reduction, all of that remains the same. Only the loss function definition is changing. So if you run a regular multiple linear regression and you see that the coefficient values are very high, then you would try out a lasso regression and a ridge regression, typically in that sequence, to ensure that your coefficients stay within a range and don't explode. And that is what this regularization does. And more details you can find in the link that is given below. More often than not, in practical contexts, you use regularized loss functions, not loss function directly. Because there may be a lot of sensitivity to one variable. The variable, even a small change in that variable sets off the dependent variable by a high amount. In such cases, by using lasso regression or ridge regression, you can find better regression models. The output is still the same. Output is still alpha plus beta 1x plus beta 2, beta 1x1 plus beta 2x2, etc. The same equation that is shown before. We are just changing the definition of the loss function that we are minimizing. Okay. Mr. Sukesh.
Sir, this normalization and here, what is the difference now in this? Because all the parameters we normalize, right? If we normalize, it will become maybe if I do normal, take the value normalize, and it will become between 0 to 1.
Yeah.
After that, are we applying this here? This parameter?
Great question. Great question. So I have, in fact, my next slide is scaling and mean value normalization. So this is what I spoke about before, where you're actually either both scaling it and then maybe even translating it to change the mean value, so that you can bring all the variables into the same range. But the answer to your question is that scaling and mean value normalization typically is done by the person or persons who are doing the exploratory data analysis and data cleansing. What you receive, you're not doing normalization as a model builder. You are, normalization is being applied because normalization is needed for every method, not just for regression. So you're doing this as part of your data cleansing. So let's say it's a different team which is doing data cleansing and a person who is receiving a cleansed data set to build a best regression model. Then for them, it is important that they ensure that the regularization is done when they observe the beta values to have a high range of variation. When the x1, x2, x3 after normalization will be in a certain range. But beta 1, beta 2 can be any numbers. They are not necessary. It's not necessary that they be values between 0 and 1 or -1 and 1. They are any numbers. So when you run a regular regression, you observe that your beta values are varying a lot. At that point, you don't go back and normalize because you may not have the sort of jurisdiction to normalize at that time. The value has been handed over to you by a domain team and you want to work with that thing. If you normalize, then it may not make domain sense for them. but you can certainly try out a regression that is regularized. So you're right that regularization and normalization have an overlapping purpose, but they are two different techniques. Normalization typically applied at the level of at the time of data cleansing, and regularization at the time of model building. So it's like a parameterization of at the time of model building.
How do you select this penalty value, Professor?
Like we did the
It's
you know,
intuition,
the
or
thing,
like, is there anything,
grid
any formula?
optimization, grid optimization. So typically, you know, let's say if your loss is what you want to give more importance for, and not so much importance for, you know, the beta, the coefficients being in a smaller range, then you might just set this up at 0.1 or 0.05, or, you know, a small number. Whereas if it is very important, if this is going to overshadow the values of the beta terms, are going to overshadow your loss computation, then you want to set this as a higher value. So depends on the problem you're solving. You can see types of problems and how much value to set in the link here.
Thanks.
Yeah. Ms. Raghuraman?
Yes, Professor. Can we kind of get a feel about where this lasso and rich regression is most applicable? Where typically in what kind of data or which kind of industry sector does this beta tend to explode? And vis-a-vis, why would a simple or a multiple linear regression not be applicable in those? So that we get a touch and feel about typically in which industry sectors or which kind of data these various regression models are most applicable.
Yes. The links that I have provided, Mr. Raghuraman, there were links on some of the previous slides also. They give you multiple examples of regression being applied. And also there are, survey papers on regression where the, practical applications, industry applications are listed with mention of ridge regression working well. For example, there are multiple automotive problems where ridge regression works very well, and this is available in the literature and at the links. If I don't know if you saw the deck I uploaded yesterday. The last slide is a collection of links on regression, so you will find this there.
Thank you very much. We'll take.
Okay. Let's move on. We have taken a good amount of time for regression. In fact, we already have passed our time for the break. So let's take the break and come back to do k-nearest neighbor. We are 84 minutes into the class. So it's 7:54 p.m. where I'm in Mumbai today. 7:54 p.m. 8:04 p.m. I'll be back.